In the last video, we talked about the relevant consequences of classical magnetism. We saw that when a nucleus with a magnetic moment is placed inside a magnetic field, it doesn't just sit still in there. It processes around the field at a frequency determined by two things: the nucleus itself and the strength of the magnet. But somewhere in the middle, I mentioned something really important. Even though the magnetic field creates these spin up and spin down states, the population difference between those states is insanely small. And that should sound really weird to you. Because if one state is lower in energy, then why shouldn't nature strongly prefer it? That's usually how the universe works according to the second law of thermodynamics. A ball thrown in the air falls back down because the ground is a lower energy place for it to be. Two magnets will snap together more easily when opposite poles face each other because that arrangement lowers their magnetic energy. Again and again, nature seems to prefer the path that brings down energy. So why aren't all the spins in the lower energy state? That question is what this video is going to address. But before we move on, I'm going to stop referring to these spins as simply spin up or spin down. Those labels were useful for building the intuition, but now they're going to start to be a little misleading if we keep using them. From here on, it will be more accurate to describe them as different energy spin states, especially once we start introducing the mathematical formalism that we use to represent spin. For example, we know that a spin 1/2 nucleus can adopt two states. Once we place it in a magnetic field, those two states are no longer equal in energy. That separation is due to what we call Zeeman splitting. One state sits slightly lower in energy, while the other one sits slightly higher. In a simple geometric picture, we describe the lower energy state as being aligned with the magnetic field, and the higher energy state as being opposed to it. But that raises obvious questions like, if the field favors lower energy states, then why do any nuclei remain in the higher energy state at all? And where are they getting the energy to do this? To answer that, I'm going to break the problem into two parts. The first is, why is the energy gap between these states so incredibly small? This here is the energy gap between the two states. Delta E is equal to h bar gamma b0. And from this equation, we can see that the size of the gap depends on two things: the gyromagnetic ratio of the nucleus and the strength of the magnetic field. Larger gyromagnetic ratios will give larger splitting, and same with stronger magnetic fields. But even inside a very strong NMR magnet, this energy difference is always extremely small. We can see why when we rewrite the energy gap another way. From the Larmor frequency equation, omega 0 is equal to gamma b0, we can rewrite our energy difference as delta E is equal to h bar omega 0. And because omega 0 is equal to 2 pi nu and h bar is h over 2 pi, we can reduce this and this becomes delta E is equal to h nu. This familiar equation is the energy of a photon. So the energy needed to move a nucleus from one spin state to the other comes in packets of electromagnetic radiation. This is light. But because the nuclear energy gap is so tiny, the photon needed to complete this transition is not ultraviolet, not visible, or not infrared. It's radio frequency radiation. This is why NMR uses RF pulses. The RF pulse supplies the needed electromagnetic radiation with the correct photon energy that matches that tiny gap between the nuclear spin states. And when that match happens, the spins can absorb energy and be driven away from equilibrium. And I can show you that with some simple math. So for hydrogen 1, the gyromagnetic ratio in hertz is 42.58 megahertz, or 42.58 million hertz. Let's say that we're working with a strong NMR with a magnetic strength of 18.8 Tesla. Multiplying gives us 800 million hertz, or 800 megahertz. And on the electromagnetic spectrum, that falls exactly into the range of radio waves. So the frequency we have to work with is radio frequency. And that also explains why the electron version of this experiment, called EPR, uses much higher frequency radiation. Electrons have a much higher gyromagnetic ratio, so in the same magnet, we would fall into the range of microwaves. Radio frequency waves would not be nearly enough to cause an electron transition in NMR, which is good because we don't have to worry about observing electron transitions. But the idea is similar. Magnetic energy levels split inside the magnetic field. Okay, now the second part of that question is, so what about these small energy gaps? What does this mean, or what does this tell us about why some spins end up in the higher energy state? And that's where the Boltzmann distribution comes in. The Boltzmann distribution tells us how particles distribute themselves between energy levels at a given temperature. This here is what we call a partition function, and we can use it to describe the statistical properties of a system in thermodynamic equilibrium. This is what we'll use to determine the probability of having a spin in any energy state. On top of the exponential, we have E, which is the energy of the state that you're interested in. For a spin half nucleus, we just have two energy states given by this formula. We label these states as Mi, as they're projections of the nuclear spin onto the z-axis. So the energy of each state can be represented by E equals negative gamma h bar Mi B0. On the bottom, we have KT, the thermal energy of the environment. So the real competition is between the magnetic ordering and the thermal randomization. But in NMR, E is so tiny compared to KT. So room temperature completely wins this competition and ruins the preference for a lower energy state. The magnetic field is trying to organize the spins, but the thermal energy is constantly pushing them back towards disorder. That's why the population difference is so small. Let's show that mathematically. If we want to describe the actual probability of finding a spin in each state, we take its energy and divide it by the partition function. So the probability of occupying a particular state is this equation here. So again, let's use hydrogen 1 in an 18.8 Tesla magnet and 273 Kelvin for T if we're at room temperature. All of this together gives us around a 50.003% chance for lower energy states and a 49.997 chance for higher energy states. So if you had 8.5 million spins, there would be only 510 more spins in the lower energy state, giving you a polarization of 0.00006. Insanely small. For example, New York City population is about 8.5 million. So imagine only 510 people doing all the work to keep the city running. And that explains what polarization is. Those excess spins are exactly what contribute to giving us an NMR signal. That tiny leftover imbalance becomes a macroscopic magnetization of the sample. So NMR signal doesn't come from all the spins equally. It comes from the tiny excess population that doesn't cancel out. So all that we just saw at room temperature, even in a strong magnetic field, that imbalance is usually just a few parts per million. And that's one of the main reasons why NMR is naturally insensitive. Not because the technique is bad per se, but nature just gives us a very small population difference to work with. Now, this also tells us how to classically improve the situation. Since we have a negative exponential, a larger exponent value will give us a higher probability for our lower energy state to be more populated. And we can get that larger exponent by having a larger numerator or a smaller denominator. If we want more polarization, there are really only two knobs that we can turn. The first is increasing the magnetic field strength. A stronger B0 increases the energy gap, like we said before, and if the energy gap gets larger, the lower energy state becomes slightly more favored. That increases polarization, which gives us a stronger signal, and is also why people prefer going to higher field NMRs for better spectra. The second knob is temperature. If we decrease the temperature, then KT gets much smaller, and that means the energy gap becomes more important compared to the thermal energy of the environment. So lower temperature also increases the polarization, but if you decrease the temperature substantially, then you're not going to be working with a liquid anymore. Your sample will freeze into a solid, and solid state NMR is a complex catastrophe in itself, so temperature typically isn't tampered with. Now there's a third factor, and that's just the nucleus itself. A nucleus with a larger gyromagnetic ratio has larger energy splittings in the same magnetic field. And that's part of why proton NMR is so sensitive. Hydrogen 1 has a very large gyromagnetic ratio. So in the classical thermal equilibrium picture, stronger magnets, lower temperatures, and working with nuclei that have larger gyromagnetic ratios all help to increase the population imbalance. But even then, the polarization is still tiny. And that's why really cool fields like hyperpolarization exist. Boltzmann stats are essentially nature just telling us, no, you cannot have nice spin polarization. If you want any better, then you're going to have to spend absurd amounts of money on stronger magnets in hopes of squeezing out a little more signal. Hyperpolarization ignores that miserable equilibrium limit and gives you orders of magnitude more magnetization instead. Hopefully in a future video, I can get an expert in the field to lecture on that. For now, what we can understand is that a magnetic field creates a small energy difference between nuclear spin states. The Boltzmann distribution tells us that slightly more spins occupy the lower state than the higher state, and that tiny population imbalance is what we call polarization. And when you multiply that tiny imbalance across an enormous amount of nuclei, you get a small but present macroscopic magnetization. That magnetization points along the main magnetic field and eventually gets turned into observable signal.